All right, let's get right into it. Welcome to this explainer on the hidden, incredibly fiery industrial journey of what is probably the single most important powder in human history. We are, of course, talking about cement. I mean, it is the literal foundation of our modern world, right? It holds our cities, our bridges, our roads together. But how often do you actually stop and think about how this seemingly simple gray dust is actually made? Today, we are going to unpack the extreme journey of cement and look at how we transform massive mountains of solid rock into a microscopic powder through a brutal gauntlet of crushing force and roaring fire. So here is our roadmap for today's journey. First, cement versus concrete. Second, raw ingredients. Third, quarrying and crushing. Fourth, the roaring kiln. Fifth, cooling and pulverizing. And finally, number 6, the scale and future. Starting off with section 1, cement versus concrete. Let's clear up a major misconception right away. Okay, the absolute crucial point you have to remember is this. Cement is not concrete, and concrete is not cement. People mix these up all the time. To understand the difference, just think of baking. Cement is essentially the flour in your recipe. It's the ultra-fine powder that acts as the binding agent. Concrete, on the other hand, well, that's the actual baked cake. Concrete is a composite material formed when you take that Portland cement powder and mix it with water to create this reactive chemical paste. That paste then binds together sand and rock, what we in the industry call aggregates, to harden into the most widely used resource in the world, right after water. So, throughout the rest of this explainer, keep in mind, we are focusing strictly on making the flour. Moving right along to section 2, raw ingredients, the elemental recipe, if you will. Cement is fundamentally a chemical formulation, and it relies on 4 primary elemental pillars: calcium, silicon, aluminum, and iron. And manufacturers have to source these 4 pillars directly from the earth. The calcium, that primarily comes from massive deposits of limestone. Silicon is sourced from sand. Aluminum is drawn from clay or marl, and the iron is extracted from iron ore. Now, get this. What I find absolutely amazing is that this specific elemental recipe was pioneered way back in the early 19th century by an English bricklayer named Joseph Aspdin. He actually made the very first Portland cement by burning powdered limestone and clay right on his own kitchen stove, literally on his stove. And from that pretty crude domestic experiment, he laid the foundation for a modern industry that today processes literal mountains of rock. Which brings us to section 3, quarrying and crushing, the industrial gauntlet. This right here is step-by-step manufacturing on a gargantuan scale. Step 1 is the quarrying. We're talking about literally blasting and extracting massive chunks of limestone, clay, and sand straight from the earth. But obviously, you can't just throw giant boulders into a furnace. So step 2 is the crushing phase. These massive mechanical crushers take these giant rock slabs and violently break them down into much smaller fragments, roughly the size of baseballs. Once we have our baseball-sized rocks, we move to step 3, grinding, mixing, and blending. The rock fragments are finely ground together, sometimes dry, sometimes using a wet process, to create this incredibly uniform mixture. And this isn't just a random mix. This precise blending is heavily monitored in laboratories to ensure the exact chemical balance of calcium, silicon, aluminum, and iron is perfectly dialed in before it faces the heat. And speaking of heat, let's jump into section 4, the roaring kiln, the fiery heart of the whole operation. The sheer scale of these operations is just wild. The perfectly blended dry powder is first transported way up into these massive preheating towers. And by cleverly using exhaust heat generated from the plant itself, these towers preheat the material, kicking off the chemical reactions early and saving massive amounts of energy. From the towers, the material is fed into the higher end of the rotary kiln. Now, these kilns are these enormous cylindrical steel tubes lined with special fire bricks. They sit on a slight incline and slowly, constantly rotate. As the raw material slowly tumbles down this rotating kiln, it gets closer and closer to the lower end, where a literal roaring flame is waiting for it. The temperature inside this kiln reaches a staggering 2,700 degrees Fahrenheit. Just let that sink in for a second. 2,700 degrees. At that temperature, the raw rock and sand don't just get hot. They actually begin to melt. They become partially molten. The heat is so intense that it forces a series of highly complex chemical reactions, fundamentally changing the molecular structure of the ingredients themselves. And what comes out the other end of this inferno? Well, it's definitely no longer limestone and clay. It is a completely new rock-like substance known as clinker. Clinker exits the kiln as these glowing, red-hot, marble-sized gray balls. It pours out looking almost exactly like a molten lava flow. The primary chemical phase created in this extreme heat is known as alite, or tricalcium silicate. This alite is absolutely crucial. It's the reactive ingredient that will eventually give our cement its incredible binding strength when it finally meets water.
All right, section 5, cooling and pulverizing, turning those rocks into powder.
So this red-hot clinker drops immediately into a clinker cooler. Here, it gets subjected to rapid cooling to bring it down to a temperature where it can actually be handled. And this brilliantly illustrates the efficiency of modern plants. That intensely hot air generated during the cooling phase, it's captured and blown right back into the kiln, which saves fuel and drastically increases burning efficiency. Once cooled, the marble-sized clinker goes into a massive ball mill. Here, it is totally pulverized alongside a small amount of gypsum, which is added to help regulate the setting time of the final product. The grinding here is so incredibly thorough that the resulting powder is practically microscopic. We're talking about a powder so fine that 1 single pound of it contains roughly 150 billion grains. That is mind-blowing. Our flour is finally milled. Finally, section 6, the scale and future. Let's talk about the global impact of all this. Look, while cement is undeniably a modern marvel, it literally gives us the ability to house billions of people and build complex global infrastructure, it does come with a colossal environmental price tag. Cement production accounts for roughly 7% of total global greenhouse gas emissions. 7%. That is one of the largest sectoral carbon footprints on the entire planet. Over 85% of these emissions come directly from that kiln process we just talked about. It's partly from burning the fuels required to reach those crazy 2,700-degree temperatures, sure, but primarily it's from the calcination of the limestone itself. Calcination is a chemical reaction that physically releases naturally stored CO2 out of the rock as a byproduct, right there inside the kiln. But the industry isn't just sitting on its hands here. They are aggressively targeting carbon neutrality by 2050. So how are they going to do it? A big part of it is through carbon capture, utilization, and storage, or CCUS. Facilities are starting to implement post-combustion capture technologies that use chemical solvents. Basically, think of them as these giant chemical sponges that literally scrub the flue gas, capturing 85 to 90% of the CO2 before it ever hits the atmosphere. They're also utilizing pre-combustion captures. They're co-processing alternative fuels, like tire-derived fuels to help reduce landfill waste, and they're pioneering new lower-carbon cement blends that use alternative supplementary materials, so they just don't need as much of that carbon-heavy clinker in the first place. Which leaves us with a massive, absolutely crucial challenge. Cement is the literal bedrock of human civilization. Our need for it, it's not going anywhere. So as we continue to build and expand our modern world, how will we successfully revolutionize this ancient, fiery recipe to completely eliminate its 7% global carbon footprint? It is a challenge of innovation, of chemistry, and of engineering that is for sure going to define the next century of construction. Thank you so much for joining me on this explainer. Keep learning, keep asking the big questions, and I'll catch you next time.